Hey everybody, today I want to show you that 2 fully divides a particular expression. Now we're talking about the natural numbers for our exponents here, so that's the positive integers. Some people like to let 0 be a member of this set, but I'm taking it just to be the positive integers, okay? Now a quick observation here, just to make it clear what we mean by this notation. 2 trivially divides, notice I use a single vertical bar. Okay, 3 raised to the 2n, and it's 2 raised to the n actually. I've got to say that carefully. Okay, and that's clear without knowing, for all n, right? For all positive natural numbers n, because this is an odd number, and an odd number plus 1 is certainly an even number, and 2 is going to divide it. The question is, we want to show that it fully divides it. And let me give you an example of what I mean by that. The double vertical bar, again, notice the double vertical bar here versus this, okay? Now, so just some examples. 2 would fully divide 18, okay? Because no higher power of 2 divides 18. 18 is equal to 2 times 9, right? So there's no higher power of 2 than 2 as far as 18 goes. Now, let's just, again, just to be sure, 2, and I use the negation of this, we'll put a slash here. 2 does not fully divide 72, right? Because notice that 72 is equal to 2 cubed times 9, right? 2 cubed times 9. So there's a higher power of 2 that divides 72. Now, just again to be certain here, 2 cubed does fully divide 72, right? So hopefully we're clear on what this symbol that's sort of uncommon means, a double vertical bar. Now, so we're going to show that's true for all positive integers, and it's really quite simple, the proof, because we have 3 squared. I say it's quite simple. There's one more step we have to take. We have 3 squared is congruent to 1 mod 4, and I'll show you why mod 4 is important in just a second. Right, 3 squared is 9, 9 minus 1 is 8, which is certainly a multiple of 4. So you see, we get right here that 3 to the 2n plus 1 is congruent to 2 modulo 4. But what does that mean? That means that 3 to the 2 raised to the n plus 1, okay, is equal to 2 plus some multiple of 4. And I'll put 4k. Now, y'all, of course, this k is going to change for each n, right? But I'm not going to, I could technically write k sub n here if you wanted to. It's something that it's going to depend on the particular n. But what's important about this? Well, this is equal to 2 times 1 plus 2k, okay? So this part, this parenthetical quantity is certainly odd, and that means that this proves our result, okay? This part right here in the parentheses is definitely an odd number, so this proves that 2 divides. In other words, this statement right here is equivalent to saying that 2 divides 3 to the 2n, 2 raised to the n plus 1, fully. And it's a nice modular arithmetic proof. It was done in Andreescu's 104 number theory problems, where he did it directly, but mentioned that modular arithmetic is the best approach. Okay, so, and it is certainly in this case. And now that I've proved it for you, I want to go back to the very beginning and talk about the technicality for n equals 0. If n is equal to 0, okay, n equals to 0 implies that this is 3 plus 1, right? And so 2 certainly does not fully divide 4. Again, y'all, n equals 0 results in this parenthetical expression being equal to 4. So in other words, that's why we started just with the positive integers. And it does hold for all positive integers. A lot of you might think this is an induction proof. It's not. It's anything but an induction proof. since we have this identity right here, it just holds for all n. You don't have to mention the word induction. Okay, it just is a direct proof that this result holds. Okay, that is all. Thanks for viewing.